All right, friends, without much ado, these videos actually have sound. The previous ones I didn't have sound. Anyway, here we go again. We're in section 3.1. This is all about the derivative, and this is how we define the derivative, the official way, if you want to think about it like that. And what we have here is I want to make sure that we get this new vocabulary word, which is called differentiation. That's the process of finding the derivative. So if we say we're going to differentiate a function, it means we're going to find the derivative of that function. There are two ways to do it. The first way I'll show you is not a way I like because it is a one-time use method. I prefer this second method here, which gives you a whole function, which lets you find the slope anywhere you want. So this first version here, we use this notation. You see there's a lowercase f and then like an apostrophe and then an a. So how we read this is we read this as f prime at a. So we call this prime, that little symbol there. And so that is the derivative at a. And the derivative, as we know here, this is our function. And we're going to plug in our point, whatever value a is. And then we add that h. Remember, h is that little tiny amount that we're going to add to make it a second point. And we compute this difference quotient, the limit of this difference quotient here, and that will give us the actual slope. It'll spit out a number for you at point A. The way I prefer is this way. We say f prime at x, which instead of a's, we have x's here, which generates a formula. So let's see how some of these work. Our first example here, my friends, will be, we're going to use this function here, 3x squared minus 4x plus 1, and we want to find f prime at 2. So what we're going to do, oh, wait a second, this is the all x method, sorry. Oh, I got these out of order. It's okay. We're going to do my method first, then we'll do the other method. So we need to do two things. We have to find what f of x is, which is right here. We already have it. And then we need to find this f of x plus h. Now remember, you've got to substitute x plus h every place you see an x. So I need to substitute it here and here. And then that's going to create some algebra we need to do here. I've got to square this binomial and distribute that 3. I've got to distribute that -4. And when I do all of that algebra, I'm showing you the algebra here. I'm not going to walk you through it, but I'm showing it to you. So if you want to pause and look at that, you certainly can. And we end up with this. This whole thing is f of x plus h. So that whole thing is going right here, minus, this is f of x. And remember, everything that's over here in f of x is going to be duplicated over here, and we're going to cancel it. So all those things are going to cancel. I see there's a 3x is going to cancel. There's a 4x that's going to cancel. And there's a 1 that's going to cancel. Notice this is subtracting. So if you wanted to, if you're saying, wait, that's a -4x, it's okay. We're distributing that negative sign, which would make it a positive. And once we do all that, we end up with this. We can cancel h's. Remember, there should be an h in every term. If there isn't, you might have done some algebra incorrectly. Once I cancel those h's, I end up with this. And I say, what's the limit of this function as h goes to 0? That means this part, this 3h right here, goes to 0. And I'm left with 6x plus 4. That's the derivative. So then we say, well, we wanted to know what was the value of this at 2. So I plug 2 in here, and I get 12 minus 4 is 8. Now, if I use the other method, you'll see there's some similarities, except we're finding it at this point A. So instead of f of x, it's f of a. And in this case, I can compute this whole value and find a number. I'm just plugging 2 into my polynomial here. Then I want to find f at 2 plus h. That's the analog of x plus h. Same thing, plugging 2 plus h in every place I see a 2. Do my work, and I get this value right here. And that gets me to this point. I can cancel the 5s. I can cancel my h's, and I'm left with this, 3h plus 8. What's the limit as h goes to 0? Well, this part goes to 0, and I'm left with 8. Notice the answers are exactly the same, my friends. All right, I will attach to this some examples for you to look at. Okay, this is some examples for section 3.1, some examples of using the definition of the derivative. So you can see here, this is checkpoint 3.3. Here's our problem. Here's our function. We want to find what is f prime at 1 using the definition. And so we figure out, we find the derivative by substituting in the x plus h into here. I do all my math here, and I end up with this big function. I do my subtraction, and I'm here. Remember, we're checking to make sure, does every term have an h? And the answer is yes. Go ahead and cancel those h's that you just found, and then we can take this limit as h goes to 0, which gets me 2x plus 3. So that is the derivative right here. And then that's f prime at x. And then we want to say, well, what's f prime at 1? I'm just going to plug 1 into here. 2 times 1 plus 3, and the answer is 5. That's the slope of this curve at x equals 1, is what that means. There, 3.4 has a physics example for us. So we have an object being dropped. This is gravity. That's the initial position. Remember, we use s for the position function, s of t, t being time. In this case, we're doing this in seconds. And just so we know, the relationship between the velocity function and the position function is that when you take the derivative of the position function, that is the velocity function. So that's a very important thing to know when you get ready to take your physics classes. So we're going to do the same thing. We're going to use our definition of the derivative to find what is the speed of this, the velocity of this object at t equals 1. So I'm plugging everything in here. In this case, we're not using x's, we're using t, so it's the same process, t plus h. So this is s of t plus h, that's this whole thing, minus s of t right here. And we take the limit of that as h goes to 0. Same process, do all my subtracting, do my canceling. I end up with this, take my limit, and I have negative 32t. I go ahead and plug in 1 second into that formula, and I get negative 32. So that's the velocity of this particle, at t equals 1. The next example is a profit curve. So we have a profit, I think it's at a bakery, and S represents the price of a scone. They're selling scones. And so that profit function is modeled this way. And so we want to know what's P prime at 3.25, $3.25. So we want to know what's the velocity, what's the slope of the profit function. And should they or should they not increase prices? Well, if you think about the profit function, you would have money, price on the bottom axis, price increasing to the right. So if the slope is up, that tells you that this function, you still have room to increase your profit. That is, as you increase the price. So if you can increase the price, you'll make some more profit. If the slope was negative, that means as you move over, you're losing profit. So as long as you can move the price over, you can make some more money. So what we're going to do is take this function and do our definition of the derivative. So P at S plus H minus P of S all over H. And we do our same math. Just the letters have changed, that's all, because we're changing the context. And so here is my profit function with the S plus H. And then we're going to subtract out the profit function here. And I end up with this right here. Go ahead and cancel your H's. Take the limit. And I'm left with this, negative 40s plus 150. Then I plug in my price point, $3.25. And I notice I have a positive slope there, meaning that the function value is going up at that point, so I can move to the next price point, 326, 330, whatever that next price point is, and we'll be able to generate some more profit.